first we have the Prim's algorithm. So the purpose of this algorithm is to find the minimum spanning tree. In the last class, I covered what is a minimum spanning tree. So minimum spanning tree is there are like many different ways to construct spanning trees from a graph, but the graph with the minimum weight of the total of the edges is considered to be the minimum spanning tree. So, so Prim's algorithm is one of the algorithms that helps find the minimum spanning tree of a graph. So the minimum spanning tree is a subset of the graph's edges that connects all the vertices together, and it does not create a cycle. So, and also with the minimum possible total weight. So the Prim's algorithm works kind of like this, that it starts with a single vertex, then it grows the spanning tree by adding the cheapest edge on every iteration or on every step. So from the tree to the vertex outside the tree. So it always goes for the vertices which are not already added to the tree. So this process is repeated until all the vertices are included in the tree. So some properties of the Prim's algorithm is it is designed for use of weighted graphs. Mark this, it's used for weighted graphs, but it is not used for directed graphs. So it has to be a weighted graph, but it is not a directed graph. So it is a not directed weighted graph. So we have the Dijester's algorithm for this, for finding the minimum spanning tree for directed graphs. But Prim's algorithm focuses on weighted graphs which are not directed. So by weighted graphs, what we understand is each edge on the graph has a numeric value or a weight. So the algorithm selects edges based on these weights. Prim's algorithm is basically a classic example of a greedy algorithm. All right. So what it does is it makes the optimal choice at each step. All right. So as it attempts to find the overall optimum way to solve the entire problem. So now let's have a look at the Prim's algorithm itself. So it starts on step 1, we select a starting vertex. Then on step 2, we repeat step 3 and 4 based on certain condition here. Right, so we're going to run step 3 and 4 until there are fringe vertices. So on step 3, we select an edge E that connects or which is connecting the tree vertex and the fringe vertex that has the minimum weight. Then we add the selected edge and the vertex to the minimum spanning tree. And we repeat this process until we have visited all the vertices. Now let's have a look at an example. So here we have a graph G. You can call this a graph G or some regular graph. So it is a weighted graph. You can see the weights on the edges, which are connecting the vertices, but it's not a directed graph. It's a not directed graph. So we're going to run the Prim's algorithm on this, and we'll create a spanning tree, a minimum spanning tree. So to keep track of the nodes which are already visited, we need to keep track here. So I'm using the visited to keep track of all the visited nodes or the vertex. So let's start with our node A here. So let's have A as the starting node. So now A is connecting B, C, and D. The weights are 2, 3, and 3. So the smallest node, the smallest weight is 2. So we select 2. So we keep B in our visited list. So we have already visited A, so I should put A on the visited list. So we had selected B because it has the smallest edge weight. So we put B here. So we go from A to B. It has the weight 2. So B is now visited. And we have selected this edge here. So now we're going to see um, what what vertices we can reach from A and B with the minimum amount of weight. So here we can see that we have C and D from A, which has the minimum value 3. So minimum in perception of, so we have A and B here. The edges which are not visited are C, C, E, and D. So the edges that you can see here are has 3 has the minimum value. We have 4 here, which is not minimum, and also this 3. So we got 3 different edges which are connecting 3 different vertices which are not visited yet. So we're going to pick one with the minimum value. So I'm going to go ahead and pick C. You can pick any of that. So once we pick C, C gets visited. So we put C in our visited list, and also we create that in this minimum spanning tree that we're creating. So we're going from A to C with the value with the weight of 3. So now we try to see from A, B, and C what are the vertices which are not visited and has the minimum value. So we can see that we have D here, which is not visited and has a value of 3. So we pick that and we go to D. Sorry, this is not going to be the edge. All right. Right. No, actually, that was the edge. So we're going to go from A to D. D has a minimum value 3. So we keep D here as visited. Then we try to see the next smallest edge. So we have E here with the smallest value 1 here. So we go from C to E with the smallest value 1. So we put E here as a visited node. So then we start looking for other not visited nodes. So we have G and F. So so there are no edges which can reach G without visiting F. So we need to visit F first. So we have this edge here, which is 6, which connects F, and it is the minimum compared to the other weights that we have. So we're going to F from C. So we put that here. The weight is 6. Now, if you look at the edges, the vertices which are not visited, we just have only one vertex here, which is G, and it can be connected from F using this weight, which is 9. So we go there using that weight. Put F here and then G. So now we have visited all the edges. We have visited all the vertices, and let's see. Let's have a look at. Sorry, this is going to be 9. So now let's have a look at the minimum spanning tree. So that's the exact tree that I drew here. So these are the basically the edges that were selected for the minimum spanning tree using the Prim's algorithm. So if you rearrange that, it kind of looks like, so that it kind of like looks like a typical tree. And that's what we have. So if you look at the total edge weight, so that's where we just add up all the values of the edge, and we get 24. So that's the minimum weight for the spanning tree, or the minimum spanning tree of that graph G.